Last video, we talked about one-dimensional smoothing spline and solved the problem with variational calculus that gave us the kernel functions as a solution. We got the nonlinear function that can be expressed as a sum of many kernel functions. So this time we're going to look at multi-dimensional spline function and see how different kernel functions arise from it. But eventually it gave us the same solution as a one-dimensional case. So let's for the problem setup, let's consider data points per data point xi and yi for I go from 1 to n. In this case, xi is going to be d-dimensional vector and yi is going to be scalar. Okay, so let me just write out the objective function we want to optimize. So let's call this guy E of f. So that's going to be our functional. So it's going to be summation I 1 to n yi minus f xi square plus j of f lambda times j of f. So the first term is still going to be the sum of residual squares. And the second term is the smoothness penalty. So here we're going to make a generalization of the smoothing spline into multidimensional case. So remember, recalling that in the 1D case, if d equals to 1, then j of f equals to the integral of the second derivative square. Okay, so that was on, and let's say this is from A to B, right? And so this is a whole domain. So A to B is a domain of the data, right? And so we have the second derivative square as a penalty. Okay, so in the d equals to 2 case, so our smoothness penalty is we're gonna make a generalization for that, right? We're gonna make this into a multidimensional case. So here we have the second derivative squared, right? But second derivative of a multivariate function is going to be a Hessian matrix, right? The second derivative will have a Hessian matrix that's going to be a 2 by 2 matrix, right? This is going to be partial. Let's call x vector equals to u and v, right? So that's going to be, so f is a function of R2 to R. So the Hessian matrix of f is just going to be partial u squared f partial v f partial u f. So that's going to be the second derivative, right? We have a matrix here. So the idea is that we're just going to penalize on the Frobenius norm of this Hessian matrix. So this is going to integrate over the domain of x. So that's going to give us so this is going to be the penalty, the smoothness penalty for the for dimension 2 when d equals to 2. Okay, so actually this span function can be generalized into any dimension, and sometimes we want to even penalize higher derivatives of the function. So this is give us the most general case. So most in general, we can for d dimension data x and with with penalty up to m's derivative. So this is what we're gonna get, right? So remember that our f is rd to r, right? So that's our function. So the m's derivative, so the first derivative, right? First derivative of f, and let me just do it this way. Uh, so gradient of f, that's the first derivative, is gonna be d by one, right? So that's gonna let me just do it this way. First derivative is going to be RD, right? And then the second derivative, that's going to be Hessian. Let me just do it this way, right? Hessian is going to be D by D matrix. And then if we do it as M derivative, that's going to give us a RD to the so it's d to the m, right? This is d to the m. So that's the dimension. And our penalty is just gonna be the Frobenius norm of that of the corresponding derivative, right? So we're just gonna penalize it as the integral of this, and then so we're gonna do f norm square. Right. So basically F norm is just like we just square each element of this of this high dimensional of this high dimensional tensor, and then sum everything up, right? So that's going to be our penalty, the most generalized case for this problem. Okay, so now so let me just write out the solution first, and then we can talk about and then we're gonna prove that later. So let me just write out the solution right away for this. Okay, so for the next part of this video, I'm just going to be focused on the thin plate spline. That is the case where the data dimension equals to 2, and we are going to only gonna penalize the up to the second derivative for this functional. So this is what the functional E of f looks like. And remember, x is two-dimensional, so it has two components, u and v. X has u and v in here. And the goal here geometrically means that we want to find a 2D surface that best capture the relationship between uv, right? So x is have two components, uv and y, right? So that's going to be a two-dimensional surface we want to fit using all the data points. Um, Okay, so okay, so first I'm just gonna write out the solution for this problem, and then we can prove it later. So the solution is gonna be look at this. So f. So first I'm just gonna say f is that we need to minimize this functional, and that gives us the solution of this, right? So it's sum of ci and the kernel function x I plus. Okay, so the next three terms here are the linear terms, right? Or it's also called affine term. So, but the first part is where the nonlinearity lives, right? So that's the sum of kernel functions that we really care about. So this is a nonlinear part, and the kernel function for this problem is going to look like this: equals to ri square log of ri, where ri is the distance between x and each data point xi. So this is also called the radial basis kernel because this ri is kind of like the radius from each data point to x. So it's called the radial basis function, or RBF. Okay, so that's going to be the solution to this problem. And now let's see how we can derive this formula. Okay, so recall last time when we derived the one-dimensional smoothing spline, we follow this procedure, right? Basically, we start with a functional j of f, and then we define the derivative, the functional derivative as this, right? So we perturb this function f with some arbitrary function h, right? And then we want this to be stationary, right? We want this limit is kind of like the derivative for this functional, and we want that to equals to zero, right? Then basically some algebra. So after some algebra, we arrived at this form, right? A to b is a integral times something equals to zero, right? So that has to hold for all h of x functions. So this thing, whatever inside this must equal to zero, right? And then we have an ODE for that. Have a ordinary differential equation that's is something like this, right? So we got the fourth derivative of f equals to sum of uh, sum of a bunch of delta functions. And then we solve this ODE, and the solution gave us the gave us the function with the sum of the kernel, right? So we got this in the end we have this sum of ci and then k x xi plus some affine terms plus a0 plus a1x, right? So that is the solution. That is the procedure we got last time. So for this time, let's not let's not do the exact same approach here, right? Instead of we're gonna use a new tool called Euler-Lagrange equation. So that is the general result for finding the functional derivative equals to zero. It's the proof of that is very similar to this, where we kind of write out this functional derivative, and then we apply integral by parts to get this formula here. And then we get it to the integral of hx times something equals to zero. That means whatever inside here must equal to zero, right? So that's gonna give a differential equation. So this is gonna become Euler-Lagrange equation for the general case, right? For general functional j of f. So that's what we're gonna do now. I'm just gonna write out the multi-dimensional Euler-Lagrange equation, and then let's just derive the solution for function f for the multi-dimensional spline function. All right, so before I'm applying the Euler-Lagrange equation, I'm just going to rewrite this functional in a little different form that I'm just going to put everything inside one integral because that's going to show come up easier. So for the first part, we can apply the tricks with a delta function to write it down in this way, right? So square delta x minus xi. And then plus and then okay, so the trick we are using here is just fx of delta x minus xi. If we do an integral of this thing, that's going to give us f of xi, right? So that's the delta function property. We're just applying that trick in here. So now we have one integral, right? One giant integral for the functional we want to optimize. And then now I'm just going to let's just write out the multivariate Euler-Lagrange equation. It has this form. So suppose that the functional we want to optimize E of f can be written in this way as an integral uh, of L of f. Okay, so the integrand can include f. The first derivative, let me just write this as u. The first derivative, the second partial derivative, and x. Suppose it has this form, then the optimal solution for this is defined this way. The epsilon so means this functional derivative. So this is going to give us the equation like this. We'll have partial L partial F minus X. I should do U here. U. Equals to 0. Okay, that's going to be our Euler Lagrange equation. It seems very complicated, but I promise that things will be simplified a lot once we plug in E of f into it. Okay, so in this case here, this integrand, this giant integrand is going to be our L, but the nice thing here is that we don't have the first derivative to worry about, just the second derivative. Okay, so first we'll have partial L, partial F. Okay, so the first only the residual square term have the function f, so that's gonna give us some and then minus 2 yi minus f of x delta x minus xi. Okay, now let's see what's the next one. Next one is gonna be and then partial L partial f u, right? That's gonna be and then the partial L partial f u it's gonna be 2 times okay, and then have the next one. I think there should be a 2 in here, right? Yeah. This is going to be 2 times. Okay. Plus last one is going to be times this equals to 0. Okay. Yeah, that is okay. That is the equation after we plug in everything. Yeah, this is still a very long equation, but the nice thing is that it is pretty symmetric, and we'll see that in a second. Okay, now what we do? Okay, is that let's just simplify this even more. So let me see what we can do. First, we can cancel out the 2, right? So that's easy. You just cancel out the 2, and then also the other thing is that for this fx, we can replace it with f of xi because remember that we are multiplying with a delta function, and delta function only going to take non-zero value as x equals to xi, right? Other fx is going to be zero anyway, so we can just replace that, right? That's not going to affect it. And then the next thing is that for these guys, right? So now we have the derivative operator, the second derivative operator on a second derivative. That's going to give us a fourth derivative. So it's going to be the fourth derivative of f. This is going to be a fourth derivative. Going to two partial of u and two partial of v. I don't think I'm putting this superscript correctly. And then this guy here is going to be fourth derivative of f, fourth derivative of with respect to v. Okay. So now let's just rewrite it. And the equation is actually not that bad. Okay. So this is going to be fourth derivative with respect to u plus fourth derivative 2 times this equals to okay, so that is the end result we have. And so this is a partial differential equation. So remember last time when we did the variational calculus, we end up have an ordinary differential equation or an ODE. Here we have a partial derivative, right? And it's actually the right-hand side looks exactly the same. The difference is it's the left-hand side here, right? So the left-hand side, last time we have the fourth derivative of f with respect to x, right? So that's one variable, but now we have the partial derivatives. Okay, I think I'm missing lambda here. This is terrible. I think lambda is added to the penalty term, right? So here we have the lambda. This also have the lambda. Okay, that's bad. That's better. Yeah, so this partial derivative, when we solve that, that's gonna give us a kernel function, just like how we solve the ordinary differential equation. But here that's this equation is a little bit tricky to solve. And let me just even simplify this a little bit more to see what happens here. So remember that in the in multivariable calculus that we have the Laplacian operator. So the Laplacian operator is defined this way. So it's defined as this triangle is Laplacian operator, and it's defined as, sorry, there's no F. So that's the operator. It's a partial derivative operator. And when it acts on function f, that's going to give us uh, the sum of the two partial derivatives, right? So that's the Laplacian of the function f. And so here we can actually rewrite the fourth derivative as this. So if we apply the Laplacian operator twice, so this is going to give us exactly left-hand side of the PDE, right? So we're just gonna distribute the terms, and then we're just gonna distribute the terms, and then that's gonna give us exactly the fourth derivative, right? Fourth f plus 2 times fourth give us this, right? This is also called the Biharmonic operator. Yeah, I actually don't know why it's called that, but that is a Laplacian square, right? We just apply the Laplacian operator twice to get this biharmonic operator here. So we can rewrite this PDE even more simplified term as lambda, and I'm gonna write this equals to sum delta x minus xi. Okay, so that's our PDE. Um, we need to solve this to get the kernel function. Okay, so maybe for the next part of the video, I'm thinking about let's just analyze the solution function fx first, and then to show that to convert it into a solvable linear system. Let's just do that first, and then maybe in the back of the video as an optional part, I can show you. I can check the solution to show that the kernel function indeed solve this PDE. But that is really not related to statistics. It's just pure algebra for those of you who are interested in this. But if you're just care about application, just feel free to skip that part. Um, so let's just do the solution first. Let's just look at the solution first for this. Okay, just recall what we did. We want to minimize the functional for this multidimensional spline function, the simplet spline function, and then we applied all the Lagrange equation, and at the end of the day, it gave us a PDE. Now I'm just going to rewrite the solution, write the solution of this PDE first. So that's going to be some CI kernel function plus. So that's going to be the solution to this, and the kernel is going to look like this. It's going to be r squared log ri squared log ri, where ri equals the distance between point x and xi. Okay, so the point of the kernel function is that it can solve delta functions. Okay, and the CI actually the coefficient is actually proportional to the residual. So it's gonna be this. It's gonna be yi minus f of xi. It's gonna proportional to that. I'm just gonna divide by lambda tilde. Okay, and the kernel function must satisfy this condition to be able to solve this PDE. So the kernel function, when we apply this to the biharmonic operator, it must give us a constant. Constant is 8 pi, I think, times delta function. So that is the solution the kernel function must satisfy. And I'll show this condition at the end of the video. Let's just accept this for a fact right now. So this is a fact. Let's just for now, let's just try to accept this, and we will show this later, right? So that part is just pure algebra. There's nothing too much to worry about there. Okay. So for this, if this condition is satisfied, let's see what that will lead us to the PD, right? We can check this. If we just apply this to f, then we don't really need to care about this fn term, right? Those are linear term. those are the things that gonna go away in this partial derivative operations. We don't need to care about that. And you're gonna have a sum. You're just gonna have and then sum of I equal to n to n. Let's just say yi minus f of xi divided by lambda tilde, and then you have the and then just put it under it lambda tilde, and then we also have the k x xi. So this thing is a constant, right? We can just pull it out, pull it outside. Maybe not that. We need to bring the summation in first and then pull it out. Right? We need to bring this operator inside the summation sign first, and then no, you just need to bring the operator to here, right? So that's gonna how it's gonna work. So sum of n equals 1. Lambda tilde, and then we'll have, right, that's gonna give us, this thing's gonna give us this, right? So what we end up gonna having is sum times 8 pi, and then delta x minus xi. Okay, that's already we already got what we want, right? It's what we left is just a constant, and so let's just figure out the constant. It won't be too hard. So so this thing, let's say around here is equals to, let me just equals to a pi lambda tilde, and then sum, and then delta x xi minus xi. Okay, that's gonna be the right hand side, which means this guy here equals to 1 over lambda, right? So which means our lambda equals to lambda tilde over a pi, right? So that's gonna be scaled by a constant, right? What we're gonna end up having. Okay, so that checks out. Okay, now let's just rewrite everything into a linear system. We can solve that. The problem can be solved. The parameters can be solved, right? So the parameters here are CI. There are n parameters here, and then A0, A1, A2, right? So it's n plus 3 parameters in total. And so remember what we did last time is that we just plug in each data point to f of x. That's going to give us f of xj equals to sum ci k xj xi a0 plus a0 plus a1u plus a2v. Okay. Now we can write everything into the matrix form here, but let's just replace this guy here first, right? Replace this with y and c. Okay, so using this relationship here, I think we can just, let me see if I can get it. So fxi equals to yi minus ci lambda tilde. Is that correct? Okay, ci. Yeah, I think that's correct. Okay, so let's just replace that, and then let's see. So that's gonna be yj minus. Let me just write out the matrix form directly for this. Um, okay, so this side is gonna be y minus lambda tilde c, right? This is n vector, this is n by 1 vector, n by 1 vector. That equals to this K matrix, a kernel matrix times C. Remember the K matrix that you have the Kij equals to Xj, Xi. Um, maybe just reverse it. Well, this kernel function is symmetric, so so it doesn't really matter, right? So just, but I'm just gonna revert Kji equals to the kernel of Xj and Xi. And then we're going to have some affine terms. Let's call this plus, let's define matrix P here. So P is going to be simple, right? P is just going to be 1, and it's just going to be 1, U, and V, right? So that's an n by 3 matrix. This is an n by 3 matrix. The K matrix is going to be an n by n matrix. Right now we can, okay, also you see here that the number of equations we have, right? So here give us n equations, but we have n plus 3 parameters, so we need to fix the identifiability problem. So we have the equal number of equations and the parameters, right? So we can add 3 more equations to it. That's going to be, we're just going to do it this way. So the 3 additional equations you can add are just like sum of I C I equals to 0, or 1 transpose C equals to 0, and then sum of I U I C I equals to 0, or U transpose C equals to 0, and then sum of I V I C I equals to 0, V transpose C equals to 0, and we combine them, that gave us P transpose C equals to 0, I believe. Yeah. And then we can just bring everything together into a whole matrix. And that's gonna give us this, right? So can combine this and and okay. Maybe for this, let me just move the terms a little bit. Let me just move C to one side, and then the parameters to one side, and the y to the other side. So that's going to be k plus lambda tilde I times c plus p times a equals to y. So that's going to be the equation. And then we're also going to combine that with this equation here, right? So this is equation 1, equation 2. Right, let's just combine these two together. So that's going to be k plus lambda tilde I. And then we have the matrix P here, I think. And then P transpose. Then here's 0 times C alpha equals to Y 0. Okay, so that's our final linear system to be solved for this problem. So this is a linear system. This is n by 3, n plus 3 times n plus 3 equations. And then this is a linear system where we can solve our parameters C and alpha for the multidimensional spline function. Okay, so now let's just do a quick summary of the smoothing spline and multidimensional spline function to see what is the general approach to solve this type of problem. So remember that the first step is that we write out the penalized regression problem. So the functional with penalty, with smoothness penalty. So remember that our E of f equals to the sum of residual square plus smoothness penalty, lambda times smoothness penalty. right? So that's our functional to start with. Then we apply variational calculus in the order Lagrange equation, namely, to find this condition, right? To find the arcmean of f star E of f. That will give us a ODE for if the dimension is one, if fx for fx, if fx is a scalar function, and then that's going to give us a PDE if fx is a multivariate function. And then solving this ODE or PDE gave us a kernel solution, right? So this is important. Okay. So solving can give us a solution. So this, I must emphasize here that both of them involve the delta function, right? Because we observed data points, the delta occurred exactly at each data point. So delta x minus xi show up at each data point. And then kernel function just shows up as a solution to that, right? So we can write the solution in this way, equals to sum of NCI kernel function kxi plus some affine terms. Uh, those are the linear terms, but the nonlinear part has the kernel function in it. Remember in one of the previous videos that we assumed the function f to be piecewise cubic function, but now with variational calculus, we don't need to do that anymore. We don't need to care about at the nodes or at each data point that the function is going to break, right? It's going to have non-continuous first or second derivative or things like that, right? Because you have a kernel function that automatically satisfies that condition. So this approach is just much more scalable to that higher dimensions. And at the end of the day, right, we can rewrite everything into a linear system with n plus 3 parameters. I think in the general case, it's going to be n plus d parameters, n plus d plus 1, I think, parameters. So that means this approach is very scalable with that dimensions that we don't have the explosion with the dimension, right? So imagine if we assume the function f to be piecewise cubic, then the cubic function with for example, if d equals to 3, then the cubic function sorry, let me do a d, let's do a larger d, right? For example, d equals to 20, right? The cubic function is going to have xi, xj, xk. That's going to give us 20 to the third, going to give us 8,000 parameters to solve, right? So that's the system will just explode when we reach to higher dimensions. But with this multidimensional spline function, with the kernel function, that's the linear system has a very nice property, right? Okay, so for the next few videos, we are just going to look at the kernel ridge regression in particular, because remember that at the end of our solution here, in our linear system, we have this equation, right? We have this k plus lambda I times c equals to y, right? So that's the equation we are solving. So this thing actually looks a lot like our ridge regression, right? So recall that ridge regression has this closed form solution that x transpose x plus lambda I beta equals to y equals to x transpose y, I think. Um, so that is our ridge regression problem, and it actually looks a lot similar to this kernel problem, except that we are replacing the design matrix with the kernel function. So that's something very important. And I'm just going to talk about that in the next few videos.